The development of artificial intelligence began as early as the 1950s. The focus at that time was primarily to enable machines to perform specific tasks such as solving logical problems, tackling university calculus, and addressing algebraic questions, which were considered impossible for machines. However, when it comes to handling larger and more complex problems, using AI to address and generalize different situations requires consideration of a vast number of possibilities. This calls for algorithms that are both efficient and accurate. In addition, the sheer volume of calculations was beyond the capacity of the computers at that time. It was until the emergence and maturity of various enabling technologies that catalyzed the rapid development of AI over the recent decades. Artificial intelligence has been applied to various fields, creating many new and exciting applications. Among them, healthcare is an important area that AI can be applied to improve quality of life. For example, IBM, as a trailblazer in AI, developed the chess-playing supercomputer Deep Blue in 1985, which defeated world chess champion in 1997, and then the question-answering system Watson in 2004, which defeated two champions in the quiz competition television game show Jeopardy in 2011. IBM Watson was extended to Watson Health, which specialized in healthcare applications. It attempted to develop a clinical decision support system that could make recommendations on treatment options for 13 types of cancer. The attempt was carried out by analyzing a wide range of medical data, including medical records, genetic data, medical literature, and medical scans. This is an important effort towards precision medicine and personalized treatment. Google DeepMind, the notable AI research lab that created the computer program AlphaGo and beat the World Go champion in 2016, has put an emphasis on healthcare AI. DeepMind developed an AI-aided eye disease diagnosis system to identify more than 50 eye diseases by analyzing eye scan images. DeepMind also leveraged AI to conduct accurate and detailed analysis of medical images, to shorten the time required to diagnose head and neck cancers and develop radiotherapy treatment plans. To apply artificial intelligence, it is necessary to thoroughly understand the application scenario and acquire the data that are relevant for modeling the scenario. A model can then be built using algorithms. Upon evaluation, it is common to find that the model is not optimal, which cannot sufficiently describe the actual situation. Repeated review of the scenario and model update are needed until a desirable version is obtained. This is indeed a typical data mining or knowledge discovery process. The scenario of interest is modeled based on some input data X, processed by some algorithm to give output data Y. For example, X may represent some symptoms or physiological indicators of a patient, and Y takes a value of 0 or 1 to indicate whether or not the patient is infected. Based on some theories or principles, algorithm is used to learn the relationships between X and Y for the given data samples, as well as the structure and distribution of the samples, to create a model that is representative of the actual situation. When there is a new input and the output is not known, the new input can be fed into the trained model to predict the output. This model construction process is called machine learning. Suppose there is a dataset, in which each sample contains the hospital and the specialty department that a patient was admitted, as well as the bed location and whether the patient had ever fallen. The dataset can be used to build a model with hospital, specialty department, and bed location as input, and whether a patient had ever fallen as output. Using the samples in the dataset, a model can be built to predict the risk of fall in a certain hospital at certain bed location. The prediction can serve as a reminder to healthcare staff or as a reference to improve hospital environment. Machine learning extracts information directly from data using computational methods. The methods can be broadly divided into two categories: supervised learning and unsupervised learning. Supervised learning is based on a dataset S which contains n samples, each with input data xi and the corresponding output yi. Yi is known, and referred to as class label, or just label. The known outputs are used to guide model construction and thus supervised learning. Supervised learning aims to learn and establish a general model relating the inputs and the outputs based on the samples in the dataset. The major learning tasks include classification and regression. Unsupervised learning, on the other hand, is based on datasets which contain input data only. The corresponding output is not known. That is, labels are not available. Unsupervised learning aims to identify the patterns and internal structures of the data samples. Clustering is one of the learning tasks of unsupervised learning. Supervised learning methods will be the focus here, and two common supervised learning algorithms, artificial neural network, ANN, and decision tree, DT, will be discussed. Artificial neural network, ANN, is a foundational element of deep learning, a machine learning method that has garnered a lot of attention in recent years. Being a biologically inspired model, ANN mimics the network of human brain neurons. Brain signal enters a neuron through dendrite. Signals reaching the same neuron from all dendrites are combined at the neuron. The combined signal is transmitted to another neuron through axon. These neuronal links form a neural network in the human brain. Analogously, ANN consists of a network of interconnected nodes. Signal reaching a node is weighted and combined with other weighted signals fed into the node. The combined signal is processed by an activation function and then output to the next node. A basic ANN consists of an input layer, a hidden layer, and an output layer. To build an ANN model, the model is trained by a dataset of samples to learn the relationship between the input and the output. For a given sample, x1, y1, the data x1 is input into the model. After the processes of weighting, summing, and activation, the estimated output y1 hat is obtained. Here, the difference between the estimated value y1 hat and the actual value y1, that is, the error, serves as a guidance based on which the weights at the input layer are adjusted to reduce the discrepancy. This process is repeated until the error drops to a satisfactory level, or does not reduce further, and the ANN model training is then completed. The goal is to train a model such that for each sample, the input produces an estimated output which is very close to the true value. However, two undesirable scenarios may occur. First, the training is not able to yield a model closely fitting the samples, and the estimated outputs have large deviations in general. This is known as underfitting. On the contrary, even the model can closely fit all the training samples. When a new sample is fed into the model, the difference between the estimated output and the true value can be very large. This is known as overfitting. ANN is a black box algorithm. Even if an ANN model has high accuracy, it does not explain the relationship between the input and output of the model. Therefore, interpretability of ANN models is generally low. A decision tree is a tree-like top-down flowchart, consisting of nodes connected with branches. The node at the top is the root node, and the nodes at the bottom are leaf nodes. Except leaf nodes, a node represents a decision to be made. For binary decision tree, each node has two branches, except the leaf nodes. Starting from the root node, the flow traverses from one node to a node at the next level, via one of the two branches based on the decision made at the node. The process repeats until reaching a leaf node, which represents one of the two possible conclusions, also called classes or labels. For example, the leaf nodes may represent the suggestion that whether a person is infected or not infected by some diseases. As an illustration, let's see how the risk of pressure ulcers in bedridden patients can be modeled using a decision tree. The decisions to be made at the nodes are associated with the factors related to pressure ulcers, such as the length of hospital stay, whether wound dressing is infectious, number of diagnoses made, whether simple dressing is made, whether there are injuries to the hip and thigh, and so on. The decision tree would perform binary classification as to whether a patient would acquire pressure ulcer or not, which correspond to the two types of leaf nodes, pressure ulcer and non-pressure ulcer. Decision trees can be built automatically using algorithms based on the data available. A tree grows from the root node, branching out to intermediate nodes, until reaching leaf nodes. The algorithms determine the decision to be made at each node, the determining factor and the condition, and the final classification decision at the leaf nodes. Common algorithms include ID3, C4.5, ID5R, and CART. As decision trees follow a flowchart to make categorical decisions, by tracing the path through which the final decision is produced. If then rules can be obtained by traversing the nodes along the path, to gain understanding about what conditions have been met to arrive at the final decision. Therefore, compared with artificial neural networks, decision trees are more interpretable and helpful for analyzing and explaining the application scenarios. When machine learning methods are used to train a model, the dataset is often divided into two parts, one as the training set and the other as the test set, at a ratio of, say, 7:3 or 8:2. The training set contains the majority. Samples in the training set are used for the model to learn the implicit relationships between the input and output. The test set is used to evaluate the accuracy of the model learned using the training set. Furthermore, the model can be evaluated using the strategy of cross-validation. The strategy divides the dataset into several parts of equal size. They take turns serving as training set and test set respectively. At each turn, some parts are used to train a model, and the remaining parts are used to test the trained model. The process repeats until all possible combinations are exhausted. The accuracy obtained at each turn is averaged to give the overall model accuracy. For example, if the dataset is divided into 10 parts, that is, 10-fold cross-validation, 9 parts are used for training, and the one left behind for testing, then the training and testing process repeats 10 times to get the average model accuracy. This video will give some examples of healthcare research projects that involve the use of AI. The projects include the prediction of postoperative mortality, perceived quality of life, and the risk of dementia. In the first example, AI is used to predict postoperative mortality after radial cystectomy, a surgery to remove urinary bladder. Radial cystectomy is a standard treatment option for muscle-invasive bladder cancer, but the surgery has high morbidity and mortality. The ability to predict postoperative mortality before surgery is helpful to determine the best treatment plan. In a research, supervised learning was used to build a binary classification model to predict whether a patient will die or remain alive in 5 years after surgery. The input parameters are gender, age, albumin level, surgical approach, tumor stage, follow-up period, and type of diversion. Various machine learning methods were used to build the predictive model. Among them, an advanced ANN showed better performance, with an accuracy of 0.8 and sensitivity of 0.86. In the second example, supervised learning was used to build a model to estimate the perceived quality of life, QOL, of community-dwelling older adults, using a dataset collected from elderly care centers. The model can be used to generate early reminders on those who may need social or health support. The dataset contained 4 types of data: personal profile, financial status, health history, and health assessment, which were taken as inputs of the model. In particular, health assessment data included basic health metrics such as blood pressure, blood sugar and heart rate, body mass index, body fat percentage, and hand grip strength. Data from pain scale and balance scale. And also the results of timed up and go test, and the 30-second chair stand test. The output of the model was the perceived QOL level, which was based on the scores of the World Health Organization Questionnaire on Quality of Life, short form. Members of the elderly care centers completed the questionnaire to determine their perceived QOL, which were classified into 3 possible levels, namely, poor, neutral, and good. The model was trained with the results of the questionnaire as labels. A supervised learning method called least square support vector machine was used, and the model achieved an accuracy of 0.74. In a similar study, AI was used to estimate the risk of dementia, based on a dataset collected from care centers serving community-dwelling older adults. The dataset contains personal data, health metrics, and data collected from various scales, such as mobility scale, nutrition scale, depression scale, and pain scale, accounting for a total of 217 input parameters for building prediction model. The dataset also contains the score of Mini Mental State Examination, MMSE, as labels. MMSE is used for screening cognitive impairment, with a score between 24 and 30 indicating normal cognition, and below 23 indicating varying degrees of cognitive impairment. Accordingly, a binary classification model, suggesting normal or poor cognition, was trained using a typical supervised learning algorithm called k-nearest neighbor. The accuracy of the model reached 0.81. Despite the promising potential of AI in improving healthcare, there are challenges that need to be addressed. We can see from the applications discussed previously that quality of data is the key. Even cutting-edge algorithms are used. Accurate prediction models cannot be built without high-quality data. When it comes to healthcare research which involves data of human subjects, since there are more normal people than patients, or people with specific health status, samples of normal people are often the majority in a dataset, which leads to class imbalance. Models trained using imbalanced dataset tend to bias towards the majority class. For example, in the quality of life prediction research we discussed, the level of perceived QOL was rated with a score ranging from 1 to 5. In the dataset, there were more samples with QOL score equal 3, and relatively few samples with the score being 1 or 5. To obtain a more balanced dataset, the QOL levels were regrouped into 3 categories only. Namely, poor, for samples with score 1 or 2, neutral, score 3, and good, score 4 or 5. In machine learning, synthetic minority oversampling is a method commonly used to handle class imbalance. The method synthesizes more samples for the minority classes, so that the distribution of the classes in a dataset can be more uniform. In addition to class imbalance, missing data is another issue affecting data quality. When too many samples in a dataset have missing values, and are thus discarded, the remaining samples that can be used are greatly reduced. The situation could be more common for datasets acquired from community through care centers. Service users may not want to provide data due to privacy, or absent from services due to forgetfulness or withdrawal from scheduled appointments. Missing data can be handled by imputation, which is commonly used in statistics, or by machine learning methods such as the k-nearest neighbor algorithm, self-organizing map, or artificial neural network. Although big data is beneficial to healthcare research, small data scenarios are also common in healthcare. In the case of rare diseases, for example, or when the data can only be collected in specific medical institutions or under specific settings. Model training under small data scenarios is particularly challenging. In machine learning, transfer learning is a technique that can be used to expand small data by leveraging data collected from situations that are not exactly identical to the target application, but somewhat similar to improve the effectiveness of predictive models. Rapid development of AI in recent decades and the innovations created have drawn considerable attention in the fields of healthcare. This video provides basic concepts of AI with a brief introduction of 2 popular methods: decision trees and artificial neural networks. It schemes through a few research projects in an attempt to offer some insights into AI applications in healthcare. The video also discusses potential challenges in applying AI in healthcare. The application of AI in healthcare is indeed promising. It is expected to pave the way for future innovations that can assist in promoting good health and well-being.